Alright, so now knowing the values for A1 and A0, we can fully determine what our solutions are in the inner region as well as the outer regions by substituting the values of A0 and A1 that we have here. Okay. Oh, wait a sec. Yes, I just noticed that this should actually, yeah, so there's actually a plus here because when I do the x, it's minus, so it's e to the minus 1 into e to the plus epsilon x, so there's a plus here. And there's a plus here, which is why this cancels with this term, otherwise the signs wouldn't have worked out. Okay, anyway, so you can double check my algebra and hopefully you'll land up at the same place. And you can also make sure that these are the solutions, I mean, to the unknown constants you would obtain by directly substituting the boundary condition at x equal to 1 in the outer solution. Okay, so now we have both the solution for the inner and the outer regions completely determined. The only thing that remains is to see if we can find a composite solution. So what that means is I have basically two approximate solutions to my problem, valid in different parts of the domain. But what we would ultimately like to have is a single solution that's valid everywhere. And this is called a composite solution, and it's possible to obtain it by basically combining the two solutions, but by making sure that we don't overcount. Right, so what we are looking for is now the composite solution. Right, and this composite solution is equal to the outer solution, and then we add to that information of the inner solution, which gives us the inner boundary structure. But we know now that the inner solution, this is near x equal to 0, right? That's the only place we had a boundary layer. But we know now that the inner solution or the boundary layer solution, as basically its argument goes towards the core, it already gives us or reproduces part of the core solution. So this means if we simply add them, we would be double counting the portion of the inner solution that matches with the core. So what we should do is subtract out that corresponding part. So we subtract out the outer limit of f inner. Right, so, and what is this? This is basically the part of the inner solution that survived when we took its outer limit. Going back here, yes, it's basically this stuff. It's b0 minus x plus epsilon b1. Right, so this is the stuff that of part of the inner solution that exists when we take the limit of x tilde going to infinity, right? And if we simply add it, this will get double counted because it's exactly matching with stuff in the core by construction. So we don't want to double count this. So if we subtract out only this part and we leave this part of the core solution intact. And that's what this negative term indicates. So let us now add up these things together, accounting for the fact that we need to subtract this out. This is basically b0, this is basically b1. This component gets subtracted out because it's what survives. Similarly, this component gets subtracted out, and so does this. And so what we have is essentially minus b0 e to the minus x by epsilon. So the purely b0 term is subtracted out by this third term, right? Plus e to the minus x plus a0 comes from the outer solution, and this comes from the leftover of the inner solution. And then at first order, we have b1 minus b1 e to the minus x by epsilon plus e to the minus x plus a1 from the outer solution. And this b0 and b1 terms are the only thing that survives from the inner solution. But now I use the fact that a0 and a1 are 1 minus E1 and minus e to the minus 1. And similarly, the fact that B0 and B1 have been obtained in terms of A0 and A1 earlier. And that then gives us the final composite solution. Which I will now write down for you. So remember, A0 is 1 minus e to the minus 1. But B0 was 1 plus A0. So I get minus 2 e to the minus 1, right? 1 plus A0 is B0 with a negative sign, e to the minus x by epsilon, plus e to the minus x, plus A0 is 1 minus e to the minus 1, right? And then plus epsilon times minus B1, but B1 is 1 plus A1, plus A1, which is minus e to the minus 1, sorry. Yes, that looks right. So this is now a full composite solution to the problem, which is valid throughout the domain. Of course, for small values of epsilon. So these terms are the e to the minus x by epsilon terms gives us a boundary layer structure, and the rest of the terms determine the structure inside the core region. And we have obtained it by first obtaining solutions valid in different parts of the domain and then stitching them together. Of course, determining the boundary layer solution in the first step involves already matching. So we already know the two solutions should merge into one another, and when we do finally stitch them together, we make sure that we do not double count, and that gives us the final composite solution. Okay, so now as we've done in all previous lectures, let's look at how this asymptotic solution for small epsilon compares to an exact solution which can be obtained, in this case analytically to the full problem, or we could also obtain that numerically. So let me quickly take you to that Mathematica sheet. Yes, here we are. So this is the problem of interest. So I just have to specify the right hand side here. You can do a direct integration to get the solution. Here I am specifying the outer solution as we have obtained it. That's our inner solution, and this is the composite solution that I just wrote down. And then let's just compare them and plot them. Oh, sorry, this is just e to the minus x. Right, this looks right. Okay, so what we're seeing here is basically the two dashed lines that you can see. Let me expand the video, the plot window. That's better. So I'm plotting f of x versus x. And the blue line here denotes the exact solution obtained analytically of the full problem without any approximation, valid for any value of epsilon. I'm now looking at the value of epsilon close to 0.1, as you can see here. And I am now comparing the exact solution in the blue line to the perturbation solutions obtained in the inner and outer regions. These are the dashed black lines. So you see there is this top black line is the outer solution. So it's clearly matching the blue line somewhere in the middle of the domain and close to the x equal to 1 boundary, where we know that there is no boundary layer. So the outer solution matches the solution well away from the x equal to 0 boundary. Near x equal to 0, it's no longer valid and shows you order 1 errors from the true solution. That's to be expected now, because we know that there is a boundary layer there. And that boundary layer region is well captured by the inner solution, which is the lower dotted dashed black line, which doesn't match the solution well away from x equal to 0, but does match it brilliantly well near x equal to 0. And finally, by combining these two solutions, by adding them and subtracting the overlap limit, we get the composite solution in dashed red lines, which is giving us an absolutely fantastic approximation, even to just first order in epsilon. Remember, we have only gone to first order in epsilon. If you go to higher orders, it's possible to get even better approximations for small epsilon. Although it's not always a good idea to take more orders, and I will comment on that in the lecture to follow, where we discuss some aspects of perturbation expansions. But for now, you see that if I take epsilon small, the smaller I go, the better the approximation is, of course. And as epsilon increases, you still do reasonably well. You can now start to see, however, that if I take a significantly large epsilon, like 0.3, the composite solution starts to deviate increasingly from the true solution. But the asymptotic, in fact, in those regions, the boundary layer stops actually mattering, and then you don't really have an outer region as much. But the whole analysis works only for small epsilon, and you can see that for small epsilon, it really does quite well. Most importantly, this example should clarify the meaning of a singular perturbation problem, where if I were to just do a naive perturbation expansion, I only get the top dashed line, which is valid only in a part of the domain. But that the problem tells me automatically, because I'm not able to satisfy the boundary condition in x equal to 0. That then leads me to do a boundary layer analysis, where I capture the solution x equal to 0 very well. But to determine that solution, I need to match it with the outer solution. And in the process, I get a solution two solutions that I can combine to get a composite expression that does a good job pretty much throughout the domain. Now, this obtaining composite solutions, the way I showed you, works, of course, if you can analytically solve the outer solution and the inner solution. There are problems, of course, where you can't solve both analytically. For example, very often you would solve only the outer solution analytically, but the inner solution is only amenable. You can only obtain the solution in the boundary layer numerically. Then to match it requires, you can't really compare the expressions analytically. So sometimes you just match the solution at a few points, and which is called patching. This is, of course, not as elegant as what we have done here. But nevertheless, there are still approaches to try and combine them and to get a composite, to first of all determine the singular solution and get a composite solution. So to be more specific, if you could not solve the boundary layer equation at x equal to 0 analytically, you could always solve it numerically, but then you would have to determine what this domain should be. So let's say we make x go from 0 to 0.2 or 0.3. Then in the transform variables, it would be x by epsilon. So for epsilon 0.1, your x tilde would go from 0 to 30. Let's say if x 0.3 was taken as the end of the boundary layer domain, x tilde would go from 0 to 30 for epsilon 0.1. And so at x tilde 0, I would put f equal to 0. And at x tilde equal to 30, I would make it equal to the value of f given by the outer solution at x equal to 0.3. And then you solve that problem numerically, and you try to combine the expressions of the inner and outer solutions to obtain a single solution. But this of course doesn't work as well, although there are various other approaches to try and match it more cleanly. But yeah, this example really does give you, I think, a beautiful illustration of how there's one solution in one region, another in the other region, and you can combine them to get a very good approximation. Okay, so with this nice picture in mind, let us end this lecture on matched asymptotics. I hope this has given you some more insight into the nature of singular problems. In the courses we do, in the examples we take up in this course, we shall not go into very complex singular problems in fluid mechanics where where you have a non-trivial coarse solution and you really need to match it carefully. But at least now, if you do encounter these solutions later on in your research or your other work, you have a basic example with which to refresh your knowledge and to basically carry the same approaches forward into maybe more complex problems in fluid mechanics, because all the basic ideas are what we have already encountered in this lecture. In this course, however, like the pulsatile problem, we would pretty much look at relatively simple problems where the core solution is a constant or something relatively trivial, and where the matching would be something almost obvious, and also the location of the boundary layer would be pretty much obvious as it was in the pulsatile problem. But like I said, in other problems in fluid mechanics, it may not be obvious, in which case we do have to follow the asymptotic procedure faithfully, and with sufficient care, the problem itself and the analysis itself will tell us where the boundary layers are located, and the matching will reveal all the unknown constants in the problem and reveal the, most importantly, reveal the boundary layer structure of the problem and show us how the problem behaves differently in different regions of the domain. And also how, of course, overall quantities scale with the parameters, small parameter in the problem. So with that, let's bring this lecture to a conclusion. I thank you for your attention, and we were now almost in a position where we can start applying the combination of scaling analysis and perturbation methods, both regular and singular, to many other interesting problems in transport phenomena. So we look forward to doing that in the lectures to come.